have been so far seeing the free energy concepts utilized in solidification, particularly during the liquid to solid transformation. We looked at various aspects such as how phase diagrams evolve, particularly looking at liquid and solid. We also saw how the isomorphous solidification takes place, how free energy composition diagrams evolve as a function of temperature in isomorphous. And we also introduced a concept called T naught, which is again related to liquid and solid. And then we extended the T naught to eutectic, and then saw what are the kind of information that we get, particularly looking at glass formation and also extension of solid solubility. And we also saw in the last class particularly on how the eutectic solidifies, particularly the coupled growth of the alpha plus beta, how do alpha plus beta together grow in a liquid matrix, how does the liquid supply atoms to alpha and beta. Let us look at peritectic today. Peritectic solidification. Peritectic solidification is a very interesting solidification process, where if you remember what is a peritectic? One of you talk. Yes, liquid plus solid gives solid. Yes, liquid plus solid one gives you second solid. That is what is a peritectic. So, L plus let us say alpha gives you a beta. This is what is a peritectic reaction. And if you look at this peritectic reaction, if you imagine that there is a liquid inside which there is a alpha, and this liquid is reacting with this alpha and beta is coming out, where should this beta come out? Where will it nucleate? When beta comes out of the reaction between liquid and alpha, where should this beta come? It should be at the interface, isn't it? So, in principle you will have the beta forming at the interface as a thin layer. This is what is beta. The moment you have a beta form at the interface between liquid and alpha, there is no more interface between liquid and alpha. So, how does this peritectic reaction continue? Because peritectic reaction is liquid plus alpha giving you beta, and the moment the initial reaction starts at the peritectic temperature, let us remember our peritectic phase diagram. This is a typical peritectic. Many of you should know this because it is a part of the iron carbon diagram, which all of you are aware of. So, let us use exactly the iron carbon itself for understanding. In iron carbon, what is the reaction, peritectic reaction, Vijayalakshmi? In iron carbon, peritectic reaction, madam, liquid plus delta gives you gamma. So, it is liquid plus delta gives you gamma. So, where are the phases then? This is the liquid. Where is delta? Delta is on the left side here. And where is gamma? Gamma is the outcome of the reaction. So, gamma should be at the bottom, isn't it? So, that means this is liquid plus delta, this is delta plus gamma, and this is liquid plus gamma. Am I right? And at this temperature, at this peritectic temperature, if I take the liquid, cool it to a temperature just below the peritectic, the moment the liquid starts solidifying, it gives out delta. This is this portion of the phase diagram. Initially delta comes out of liquid, and that is how you see delta inside the liquid, and as you continue solidification to lower and lower temperature, more and more delta comes out, isn't it? And we can find out the volume fractions of this, not the really the volume fractions, the weight fractions, because phase diagram does not give you volume fraction. I think this you must be aware of by now. phase diagram cannot talk about volume fraction, because phase diagram the x axis is basically a weight fraction of x, is not it, or atomic fraction of x. So, volume does not come into picture. How do you get then the volume fraction of a phase? By using the density. If I know the density, and if I do the microscopy, what is that I will get? For example, if I have a two phase mixture and I do a microscopy, what is that fraction that I get? Volume fraction? You get actually the area fraction, because you are seeing a 2D section, you are actually not seeing a 3D. So, any microscopy will only give you the area fraction, and again from the area fraction you need to convert it to volume fraction. Again certain assumptions, there are ways to convert quantitative. There is a book called Quantitative Metallography, if you are interested please read that. So, where they talk about how to convert area fractions to volume fractions. Certain assumptions of course are involved. If you assume it to be a spherical particles, then it is easy to convert area fraction to volume fraction, otherwise it is very difficult. For example, you think of a plate of a second phase in a matrix, and if you cut the plate like this, then what you see it as a needle, is not it? You are not actually seeing a plate, you see it actually as a needle. So, this needle area that you are seeing, if you want to convert it into volume fraction of the particular second phase, it is not so easy. If it is spherical particle, it is easy, because whenever you cut it you basically get circles, depending on where you cut it you get different diameters of the circles. So, that is why all conversions of area fractions to volume fractions are much easier if you have a spherical particles, but real life you do not see spherical particles all the time. So, that is why one need to do some geometric approximations, and people regularly do it. There are mathematical ways of doing all this. So, you should remember that our microscopy always gives you area fraction and our phase diagram always gives you weight fraction. Okay. And so, the moment you reach this temperature, you have basically liquid plus delta of certain amount of liquid, certain amount of delta, depending on that particular phase diagram, which can be easily found out by what? How do you find out the weight fractions in a phase diagram? Lever rule. So, you use the lever rule, and from the lever rule one can find out. Now, this plus liquid plus solid, liquid plus delta is undergoing a reaction and giving you gamma, because I am at that temperature just below the peritectic. Now, what should happen in a peritectic reaction? Liquid plus delta should completely vanish at the end of the peritectic reaction, and only gamma should be left out. That is what is a peritectic reaction. But what we are seeing here is, the moment there is a reaction, the gamma that forms here, okay, I will write it as gamma here for the sake of that particular case. So, this is what it is. So, liquid plus delta giving you a gamma, the gamma that comes out covers the whole of delta, because that is where the reaction is occurring. So, the moment the delta is completely covered, there is no possibility of this further reaction between liquid and delta to take place, so that liquid slowly shrinks and delta also slowly should shrink, such that the gamma should encompass both the liquid and the delta. And for that to happen, you need the reaction to continue. How does the reaction can continue when there is no interface at all available between delta and gamma, delta and liquid? This whole problem of peritectic is what actually leads you to cases where peritectic reactions are very, very slow. That is why sometimes you may, if you cool this steel faster, you may even end up in some delta left out at the end of the solidification, because the reaction, peritectic reaction, has not actually gone to completion. There are certain phase diagrams which are full of peritectics. Do you remember any such phase diagram? We usually use a term called cascade of peritectics. Oh, you have gone too far off. I do not know about uranium, but something which metallurgists are commonly aware of, which is a very important system for commercially. Copper zinc, copper tin, there are a lot of peritectics. In fact, the system has only peritectics, copper zinc, if you look at it. It has nothing else in the liquid to solid phase transformation. Of course, in the solid state you may have something else, but in the liquid to solid you have variety of. So, the various center metallics that you see, beta phase, gamma phase, epsilon phase, all these phases come out of the peritectic reaction, and because of that you will see many of these reactions are very, very slow. Now, try to understand how does this reaction proceed. To understand that, again let us use our free energy concept. Yet at this temperature, I am sorry, it is not horizontal. At this temperature, if I draw the free energy composition diagram, all of you try to draw it, let us see how it should look like. What you have a delta here, you have a liquid plus gamma, gamma and liquid plus gamma. How many phases are involved in this? 4 phases. How many phases are there at that temperature? If I want to draw a free energy composition diagram, I need to know how many phases are there. 3 phases. What are the 3 phases? Liquid, delta and gamma. So, let us try to draw. So, there is a delta, there is a liquid, there is a gamma, is not it? So, in principle you have a delta plus gamma equilibrium, you have liquid plus gamma equilibrium. So, this is the delta phase, this is the gamma phase, this is the liquid phase, and these compositions that I am getting are what? This is the composition of delta in equilibrium with gamma. So, I can say that this is composition of delta in equilibrium with gamma. This is composition of gamma in equilibrium with delta. Am I right? And this is the equilibrium of gamma and liquid. So, this is the composition of gamma in equilibrium with liquid, and this is the composition of liquid in equilibrium with gamma. And where do you see them on the phase diagram? You will see exactly here, this one, this one, this point is nothing but the composition of delta in equilibrium with gamma. So, this is actually this composition, and this composition is the composition of gamma in equilibrium with delta. That means, in principle it is that composition, and this composition is nothing but the composition of liquid, I mean gamma in equilibrium with liquid, because this is the gamma phase. So, that composition is in principle this composition, and then you get another composition which is the composition of liquid, because everything is liquid on this side. It is the composition of liquid in equilibrium with gamma, and that turns out to be nothing but this. If you draw everything to scale, you would exactly get these compositions reflected there. I have not drawn to scale, that is why I need to do this. So, you can see that these 4 compositions, that is why whenever you draw a free energy composition diagram, it should completely reflect the phase diagram. This has to be, at least at the end of this course, it should be very clear to you. So, now if I get these things, how do you understand this? How is it useful for us to understand the peritectic reaction? What you see here is, if I now draw a small segment of this, take a finite element from this and try to look at it. What you have is, you have a delta. If I draw something like a distance as a function of distance, you have a delta phase, you have a gamma phase, you have a liquid phase. Am I right? So, liquid and delta are separated by a gamma. And now, if I look at what is the percentage of B, that means composition of each of these phases, if I try to look at how do they look like. For example, there are 2 interfaces here. One is a delta gamma interface, one is a gamma liquid interface. At each of the interface, there are 2 phases which are in equilibrium. At this interface, delta and gamma are in equilibrium, at this interface gamma and liquid are in equilibrium. If I look at this equilibrium first, delta and gamma equilibrium, I need to look at what is the composition of delta in equilibrium with gamma and what is the composition of gamma in equilibrium with delta. If I look at that, I get that compositions from here. So, if I look at those compositions, composition of delta in equilibrium with gamma and composition of gamma in equilibrium with delta, this is an increasing percentage B. Am I right? So, that means the composition of gamma in equilibrium with delta is higher than the composition of delta in equilibrium with gamma in terms of percentage B. Am I right? So, in such a case I can put these two compositions somewhere here. One, I will call it as composition of delta in equilibrium with gamma, composition of gamma in equilibrium with delta. Whatever scale that you choose, I am just schematically drawing them. Now, if I look at the other interface, which is the gamma liquid interface, I get two other compositions. One is the composition of gamma in equilibrium with liquid, another is the composition of liquid in equilibrium with gamma, and those two compositions and if you carefully look at it, the composition of gamma in equilibrium with liquid is higher in B content than the composition of gamma in equilibrium with delta. Am I right? So, as a result, this composition C gamma liquid is going to be higher than this value, and then the next one is further higher. So, I can call this as C gamma liquid, I will call this as C liquid gamma. Now, if I do a kind of a profile, I can see the composition profile is something like this. I really do not know whether this is continues horizontally into this, let us not bother about it. In principle, it may not. Why? If you carefully observe, what is the composition of liquid with which we have started? We have started with a peritectic composition. At the peritectic temperature, what is the composition of the liquid? It is decided by the peritectic horizontal. At the peritectic horizontal tells me that this is the composition of liquid, which is reacting with this delta and giving you this gamma. Am I right? So, that means this is the composition of liquid in principle which is actually reacting with alpha, and at this delta, at this temperature the composition of actual liquid is this, and that is different from the liquid which is actually interacting with that. If you want to have an equilibrium between that, you should think of that. So, in principle this liquid composition throughout may be exactly that, or might fall that far from the equilibrium, far from this interface, the liquid composition may be this composition. If you have a very slow cooling conditions, that you will see all the liquid will have the same composition as that of this. This is what we call it as equilibrium. If not, you may see that if there is a, that is why we talk about coring. So, if there is no equilibrium, then you will see the liquid composition at the interface will be this, but far away from the interface will be this, but otherwise you can assume to be that. But we are not bothered about that particular part more. What we are bothered about is here. We are saying that if peritectic reaction has to happen, what should happen? If peritectic reaction has to complete, then what should happen? This gamma should grow like this, should grow in this direction and in this direction, such that it absorbs all the delta, it also absorbs all the liquid. That is when we can say peritectic reaction is complete. So, that means the gamma should grow in both the directions. And how does this grow? We are saying that there is no interface between liquid and delta left out. If there is no interface between liquid and delta, for the gamma to grow, the only way is by diffusion of atoms. How does this happen? To understand this, we look at each of the interface. For example, if I look at the interface of liquid gamma interface, at the liquid gamma interface, if I look at it, liquid has higher B content than the gamma. So, what happens is, in order to for the peritectic transformation to complete, because why this has to happen? Because at that temperature, for that alloy composition, liquid is not stable, is not it? If I am at this temperature, for that alloy composition with which I have started with, what is stable is only gamma thermodynamically, that I can clearly see here. My alloy composition is somewhere here, I am choosing the alloy composition this, and if I carefully observe, this is the delta phase, this is the delta plus gamma phase, this is the gamma phase, this is gamma plus liquid, and this is the liquid phase. Am I right? And my alloy composition is falling within the gamma, that is what it is falling within the gamma. Because it is falling within the single phase gamma domain, at that temperature what is stable is only gamma in principle. So, whatever liquid that is there, whatever delta that is there at that temperature at a particular point of time, they are only metastable, they are not stable. So, in principle that liquid wants to get transformed to gamma. Similarly, delta also wants to get transformed to gamma. And how does this happen? This happens by the process of this liquid, it wants to transform to gamma, and gamma cannot take more percentage of B. Gamma can take only this much of B. According to the equilibrium, the composition of gamma in equilibrium with liquid is only this much, and liquid has this much of B. So, what happens is the liquid gives you gamma, and the excess B atoms are given out. That means, what happens is this liquid wants to transform to gamma, but in the process it has excess B atoms. It is something like you have seen earlier, when a liquid transforms to a solid, there is an excess enthalpy that is available in the liquid. This enthalpy is given out, this is what we call it as recalescence, is not it? Enthalpy of fusion. Exactly similar here, the number of B atoms in the liquid are higher than what a gamma can take. So, this excess B atoms are rejected out of the liquid, and where do they go? Because there is a gradient inside the gamma, the B atoms will flow towards the gamma delta interface. So, this excess B atoms that are available will flow towards this direction, because there is a gradient that is available. And now what happens is, once these B atoms reach this, before that what has happened, a small volume fraction, some small volume of liquid, a small delta x of liquid has got converted into gamma of the same composition as that of gamma, and whatever excess B atoms that the liquid has, it has rejected them out, and those B atoms have started moving towards the beta, towards the gamma delta interface, and this small region has got converted to gamma. And what has happened in that process? The gamma has got extended into the liquid, some liquid has got converted into the gamma. And now what happens is, once these B atoms reach this interface, if you look at the delta composition is this, delta has a smaller B content, okay, than the gamma, is not it? And this is the composition of delta in equilibrium with if this delta has to get converted to gamma, it needs more B atoms, because this is the difference in the B atoms between delta and gamma. So, if the delta takes B atoms, delta has certain structure. In our particular phase diagram, delta has a BCC structure. This BCC structure takes away carbon atoms, in our case B atoms means carbon atoms because we are talking of iron carbon phase diagram. So, this delta takes carbon atoms, and the carbon content in the delta raises to that of the gamma at that particular temperature according to the equilibrium. The moment the carbon content of the delta reaches that of the gamma, suddenly that particular delta gets converted into gamma. It is only a structural transformation now. Composition of the delta becomes equal to the composition of the gamma, and once the compositions reach same, suddenly there will be a BCC to FCC transformation, and that means a small amount of delta got converted into a gamma, and as a result you will see a small volume here gets converted. And what is the process? The delta takes B atoms and gets converted to gamma. For the delta to get converted to gamma, it needs excess B atoms, because it has low B atoms, low carbon content. So, and that delta, once the carbon atoms are provided to it, it can get converted to a gamma. And in the process, if I add these two reactions, what you see is basically is that liquid plus delta gives you gamma, because the B atoms which are here on this side and the B atoms that are here on this side will get cancelled. So, you see that basically the same eutectic reaction is taking place in two steps, and this is what we call it as peritectic transformation. We do not call it anymore as a reaction, because there is no reaction here. So, the peritectic reaction that we traditionally call is only at the beginning of the reaction. At the beginning you have a reaction, because there is a real interface between the liquid and the solid phase, and there is a reaction that takes place, and once the reaction takes place, there is the third phase, which is the product phase of the peritectic reaction, comes and covers the solid that is already available, and once this covering takes place, then the further reaction can only occur by diffusion. And diffusion where? Diffusion inside that product phase that has formed. The diffusion is taking place inside the product phase, and which is a solid phase, isn't it? And we all know diffusion through solids is more difficult. Diffusion inside the liquid, peritectic reaction is very easy. Why? Because all the diffusion of atoms that is happening, if you remember this, the alpha plus beta, we said liquid, all the atomic movement is taking place inside the liquid, and then they both are moving faster. That is why eutectic reaction is definitely much faster than a peritectic reaction. A peritectic reaction needs a diffusion of atoms through that solid layer, and once you understand this, you would see that it is very easy to understand the peritectic transformation. And that is the reason why sometimes you actually see, if I cool a system very fast, you may not see a peritectic reaction taking place. For example, there are what are called metastable. Is this very clear to you now? How does this happen? So, you can see at the liquid gamma interface, liquid, a small fraction of liquid transforms to the delta to the gamma by releasing B atoms, because gamma cannot take as many B atoms that are available in the liquid. So, the excess B atoms are rejected out, and small volume of liquid gets converted to gamma, and in the process now the B atoms that are rejected out travel through the gamma and then reach the gamma delta interface and get added to the delta which is available, and the carbon content of the delta raises, or the B content of the delta raises in such a way that some part of the delta get transformed to that, and all this is driven because of the diffusion. And again we all know J is minus d dC by dx. Now, what is the dC by dx here? What is the dx? Dx is nothing but the thickness of the gamma, am I right? Dx is the thickness of gamma, and what is the dC? dC is this composition difference, the composition difference between the C gamma liquid and C gamma delta. So, delta C for our case here is delta C is C gamma liquid minus C gamma delta. That is what actually drives. And again, if you look at this difference at the peritectic temperature is what? Is 0. At the peritectic temperature this difference is 0, because both of them are meeting here. At the peritectic temperature all the three are in equilibrium. So, there is a single common tangent for all the three phases. So, the composition of gamma in equilibrium with delta and the composition of gamma in equilibrium with the liquid is always the same, and if that is the same, then this is 0. If this is 0, the gradient is 0. If the gradient is 0, the flux is 0. So, there is absolutely no possibility of any peritectic reaction to occur at the peritectic temperature. You need to come below the peritectic temperature, and again the way we have talked in the case of eutectic, the lower the temperature that you come below the peritectic, the more this widens. So, the higher undercooling that I provide is useful, keeping again at the back of our mind diffusivity always plays a role, because this fellow is sitting here. So, as long as I remember that, so I know that the higher undercooling increases this, and when it increases you will see definitely this increases. If this increases, flux increases. And but there is one more issue here. The second issue is, as the transformation progresses as a function of time, what is happening? Now, as a function of time, if you carefully look at it, the gamma is becoming thicker. The gamma is growing both in this direction and in this direction, because a small amount of liquid has got converted to gamma and a small amount of delta got converted to gamma. So, what is now the gamma thickness? Gamma thickness is thicker than what it was before. So, if the gamma thickness is increasing, in our this equation the denominator is increasing, dx is increasing. If the dx is increasing, obviously the gradient decreases, and in the gradient, if the transformation is taking place at a fixed temperature, dc is always constant. The delta c which we have written here is only dependent on the temperature, because at a given temperature the phase diagram tells you what is this composition, what is this composition. Once I fix up my temperature of transformation, that means I have undercooled the liquid to certain extent, and there the reaction is taking place. Then if that is taking place at that temperature, you would see that in principle at that temperature these two compositions are fixed, and that means the numerator is fixed, but the denominator is now increasing as a function of time. That means peritectic reaction slows down as a function of temperature, time as a function of time. So, you see that initially it starts at a faster rate, but as a function of time you will slowly see it decreases. That is the reason why at very high undercoolings, if you give, there may not be any peritectic reaction significantly occurring, because at that temperature d itself is slow. D is slow and this is larger. So, both of them will lead you, and this is something which we need to understand. Now, this leads us to what are called metastable phase diagrams. What is this metastability that you get in? Because these reactions are slower, for example, liquid to react with the delta to give you gamma is not easy, because liquid has a different composition, gamma has a delta has a different composition, and the resultant gamma has still different composition, and the structures are different, and also this reaction needs essentially a diffusion through the solid state, and because of which there can be situations where the reaction may not occur at all, and that can be easily understood if we can look at this phase diagram a little more closely. If I simply look at this phase diagram and extrapolate these two curves, what are these two curves? What is this curve? Can you tell me? Solidus? Solidus? Sure. And what is this curve then? Solidus? Both are solidus. What is the definition of solidus, Prerana? I am sorry to ask you at such a late stage of your life. What is the definition of solidus? Boundary. Can you tell it in the form of a sentence? Put your words together and then frame a sentence and tell me what is solidus. Anybody else who wants?
Separates one solid and solid plus liquid.
Okay. And if I ask you to think of some other definition for it?
The composition which is in equilibrium between liquidus plus solid and the liquid.
Composition you are saying equilibrium with liquidus.
Liquid and solid.
Okay. Then what is the liquidus? It is also the same?
Given composition,
Yeah, again.
the given composition, the lowest temperature at which any liquid exists.
Yes. The temperature at which the solidification is complete. The temperature below which there is no liquid that exists is the solidus. Okay, where the solidification is complete. And what about liquidus then?
Where solidification
Starts. Where the solidification starts, the temperature below which you start seeing the solid first from a liquid. If that is the case, now what are these phase boundaries? Again look at it. This is liquid. What is this? This is delta and this is gamma. What is this? It is a solvus line. It is not a solidus line. Please understand. And what is the solidus here then? Can somebody draw it? Let me see. Okay, and why don't you put down the phases? Then it becomes easier for you. What is there on the right side of gamma? Okay. So, what about this portion of the peritectic? That cannot be called
as
solidus. Okay, you are right. Okay, this is what differentiates between a eutectic and a peritectic. Let us draw again a eutectic for the sake of argument. Now, on this, Bala, can you come and draw what is the solidus here? Not gamma, alpha. Good. Yes, that is it, perfect. In a eutectic phase diagram, the whole eutectic horizontal becomes a part of the solidus, whereas in a peritectic only a part of the peritectic falls into the solidus and the remaining part does not, because below this line you still have the liquid left out. If some liquid is left out, then obviously it is not a solidus line, and liquidus line is easier, the top portion. Similarly, here also the liquidus is easier. The only confusion that comes always is with the solidus. Now, let us come back to our question with which we wanted to start. Again I may have to re-raise this a little. Okay, let us do that. If I extrapolate these two curves, which is this is the what is called the gamma, this is gamma plus liquid. So, this is the liquidus we call it as what liquidus is this? It is called gamma liquidus. This liquidus is called the delta liquidus. By now you should, because we are talking more and more about equilibrium of liquid with one phase. So, you should slowly start understanding, because possibly earlier when you were talking of phase diagrams you never talked about gamma liquidus and delta liquidus. Similarly, when we talk about this liquidus, this is the alpha liquidus, this is the beta liquidus, though both are liquidus, but the liquid on this side is in equilibrium with alpha, liquid on that side is in equilibrium with beta. So, these things have to be ingrained into you as you go along. So, what we see is that whenever this reaction is very difficult, the system chooses any one of the two cases, either it will become like this, or it will, if I draw, or maybe here itself I will do, you will reach a situation something like this. Depending on which phase is more difficult to nucleate from the liquid, depending on the structure of that particular phase, whether gamma or delta is more difficult for it to nucleate, the system will choose that particular phase which is easy to nucleate, and when you cool the liquid rapidly, only that phase comes out rather than one phase coming out first and that reacting with the remaining liquid giving you the second phase. You will see that the whole phase diagram gets converted into an isomorphous type of a phase diagram. You see that, for example, here if I, unfortunately I do not have color chalks, if I have, I would have been easy. You will see that this gets converted into a kind of an isomorphous. You say this is a liquid delta isomorphous. So, the liquidus of the delta liquidus I will extrapolate, the solidus of the delta I extrapolate, and when both of them meet at some place, that gets converted into a liquid delta. And now, if you cool this liquid rapidly, you will see simply only delta coming out, and if I can calculate what is called the T naught curve for the liquid delta T naught curve, and if I do my undercooling such that I am below the T naught, I will get a partitionless solidification where liquid transforms to only delta, and in principle after the reaction is over I will see only delta, there is no gamma at all, provided my cooling rate is fast enough that there is no time for such a reaction to occur. And in principle, if gamma formation is more easier than a delta formation, if the structure of that is such that, I am simply giving some example, I do not know what is gamma, what is delta, let us not simply relate it to iron carbon phase diagram, they can be any phases. If that is the case, then what you will see is that there will be a extrapolation of this into that, such that when I am cooling this liquid, what I simply get is the gamma directly. That means, I need to undercool the liquid below this equilibrium liquidus to a lower equilibrium liquidus, which is a metastable liquidus between the liquid gamma phase equilibrium. That means, this is the gamma liquidus. If I extrapolate wherever this gamma liquidus goes, and if I can bring the liquid below the gamma liquidus, if my undercooling is such that I come to below the gamma liquidus, then in principle gamma can nucleate out of the liquid. And if I undercool to such an extent that I am below the T naught curve, this is now what is the T naught? This is the T naught for gamma for me. The earlier T naught that I have drawn here is the T naught for the delta. If you want, I will draw it a little more carefully, too many curves possibly confusing you, that is why I should have some color chalks. Okay. So, this is what is the T naught gamma. This is the T naught gamma, and if you extrapolate this, what you get is T naught delta. So, depending on where you are, okay, you can get basically any of those phases, and if I can undercool below the T naught of gamma, then in principle yes, I can get a partitionless solidification of liquid giving you single phase gamma. Thank you. So, you can see clearly now this is extrapolation of this is what is the gamma liquidus for me, and as a result this would be for me, and for be very careful, these two lines have to meet at a point. Ultimately what is the left axis? It is a pure metal for me. That is why if you remember in the question paper that you had, possibly in the next class we will take up that question paper and try to solve that. So, you should see that these two ultimately should reach the same point, and this is the T naught that we are talking about. And now if I look at the other phase, this is the and you can see, and you will have another, that is the T naught of the delta. So, depending on my undercooling and also depending on which phase is easy to nucleate, I may get a partitioning solidification with partitioning giving you either delta or gamma, or solidification without partitioning giving you either delta or gamma. So, you can see that a normal phase diagram now, okay, some of them get suppressed. For example, one simple easy similar thing, I can even see this. There is a very famous phase diagram called magnesium silicon phase diagram. Anybody knows about it? There is an important phase in magnesium silicon phase diagram which is very important for aluminum alloys particularly. What is that? Mg2 Si. Good. So, Mg2 Si, if you carefully look at it, okay, there is a Mg2 Si here. I am sorry, then it should be here because it is Mg2 Si. So, Si is 1. So, we are on this side only, okay, and then this is silicon, and you have a eutectic between these two. This is the typical magnesium silicon phase diagram with a Mg2 Si at the. And now, if I take this alloy Mg2 Si composition, and if the Mg2 Si crystal structure is such a complicated crystal structure that I am cooling this liquid very rapidly, and so the nucleation of this Mg2 Si is very difficult, then what should happen to that liquid? That liquid will not give you Mg2 Si, and as a result what happens actually is that this liquid gets undercooled to such an extent that if I extrapolate this liquidus curves, I get another liquid there, another eutectic there, and this eutectic that you generate is a metastable eutectic. If this phase does not form, if it cannot form because of any reason, then you see that the liquid gets undercooled and becomes stable, and to such an extent this liquid can easily become a glass, because that liquidus now is closer to the Tg, let us say, then it can easily become a glass. So, there are many phase diagrams where, particularly when there are intermetallic compounds, they do not form and suddenly that liquid becomes a glass. So, this is what is metastable phase diagrams, which is very important. Thank you.